think so why so you know the depending on the type of production or the method of production of hydrogen is considered as three different category called blue hydrogen, yellow hydrogen and green hydrogen. I am going to talk about a method which produces green hydrogen, which is called photocatalytic process. Briefly, to talk about the steps involved in photocatalytic the hydrogen production. The first one is the source of energy, which we used to assume the sunlight as the source of energy. So the energy in form of photon, which comes from the sunlight, falls into the photocatalytic materials. When it absorbs the photon or in form of energy, the electrons jump from the valence band to the conduction band. Of course, the energy required will depend on the gap or the band gap or the distance between the valence band and the conduction band. And once the electron jumps to the conduction band, if there is a reaction medium, it will take part in the water splitting reaction. So this is the basic steps. There are challenges associated with the process. The first one is the energy required for the electrons to jump from the valence band to the conduction band, which in the other way we used to call band gap. When band gap is large, which is true for most of the semiconductor catalyst, the energy requirement is large. And that energy used to come from only in UV light. And as we know, 5% of the sunlight is only UV, 50% is visible. So most of the semiconductor catalysts are UV active catalyst. That means they can use only 5% of the sunlight. That is one of the challenge. Then the next challenge is once the electrons is jump to the conduction band, if there is no reaction, it will come back to the valence band and then there will be no reaction. So that is called recombination of electrons, which significantly reduce the efficiency. So our objective is to address these two challenges. One is how to reduce the band gap so that the catalyst which is currently UV visible can be visible light induced catalyst. Then the second one is how to reduce the recombination. So just to give an example, like I told, is it possible that when a catalyst is UV active, can we make it visible active? This is one such example, TiO2, which is well-known photocatalyst because of many advantages, is UV active. But when we change these two, like a black TiO2, if we can prepare from the TiO2 which is both visible as well as UV active. So by changing the morphology, by changing the characteristic of the metal, we can change the activity of the catalyst. The second one is electrons and hole recombination, which we also try to address in this. And finally, this catalyst which we prepared, we are trying to use it for the production of hydrogen by splitting water. So Fe-doped SnO2, which we have used in this work. Why? Because this is well reported before. Fe-doped SnO2 is a well-known catalyst which is used by many researchers for the degradation of dye. So metal doping introduced the metal which is Fe here, which is a well-known dopant, will create a mid-gap energy level which alter the metal oxide band gap, resulting in high visible light absorption. Otherwise, SnO2 is UV active. Okay, unless we will dope with some metal which will reduce the band gap and active in visible light, again the problem will remain same. So these are some of the examples which I have mentioned here, which is well explored before. What we have done is we have used a different method for preparation of the epidoped SnO2, and our main objective is to reduce the band gap so that it will be visible active. So we have used the stannous chloride with 5H2O and ferrous nitrate as the precursor for the preparation of the catalyst, which we added to 200 micromole of hydrochloric acid and 32 ml of methanol under continuous stirring. After that, we shifted this solution to a stainless steel autoclave where we wanted the reaction to be happened at high temperature and pressure. So the pressure we maintained is 100 psi, and the temperature we maintained at 180 degrees Celsius for 12 hours. Once the reaction happened, then we cooled down to room temperature and then dried it at 60 degree overnight. While preparing the catalyst, we used different weight percentage of the dopant. Like there are 4 different weight percentage which we have used, which is mentioned in the right: 2.5, 5, 7.5 and 10 weight percent. We wanted to find out the effect of the dopant concentration on the band gap. Then we use this photocatalyst for hydrogen production. So this is the schematic given for the hydrogen production. Water catalyst taken in a conical flask, which is 250 ml conical flask. We have taken 150 ml of the solution of the mixture under stirring and subjected to sunlight. Then we collected the gas using a Tedlar bag, which we again analyzed using the gas chromatography with TCD detector. So this is the result from our photocatalytic experiment. What we observed that the 7.5 weight percent iron catalyst produce the highest amount of hydrogen, which is mentioned here. You can see the top one. I will talk about why 7.5%, that we also justified in terms of the characterization, that I will come to. Then of course you can see the 10% Fe gives the minimum. What we trying to find out is when we dope with Fe, whether Fe is really present in the composite, and in what form, whether it is Fe in metal form, whether it is FeO2 or anything else. So to do that, to confirm that, what we did is we did XRD analysis, and we saw that all the peaks which present for the iron is for Fe metal, not Fe2O3. So no peak for crystalline Fe2O3 is observed. So Fe is associated with SnO2 crystal. We also did the SEM analysis to find out the morphology and also the size of the particle. What we observed that these particles are agglomerate, which we can see. Then we also see that the particle size has minimum when we have 7.5% of weight percent of Fe2. And that is probably one of the reasons, because when the size is small, the surface area is large, so more production of hydrogen. We also used UV DRS to find out whether, because one of our objective was to reduce the band gap, whether we really reduce the band gap. So what we did is we analyzed the sample using the UV DRS, and the results are shown. So it shows that pure SnO2 has a band gap of 3 electron volt. That is why I told it is UV active. But when we started doping, we could see that the band gap reduced to 1.6 electron volt, which is at 7.5 weight percent, which is clearly visible active. So that is one of the reasons why we got maximum amount of hydrogen at 7.5 weight percent. We also did, then another objective I also of our study was to see that the recombination is reduced. So the recombination we have studied using the photoluminescence spectra. PL spectra of all the samples we have analyzed, the lower PL intensity in a Fe-doped sample indicate the reduction in the recombination. So the lower curve was the one which is for 7.5 weight percentage, where you can see the peak is the smallest. So that means the recombination also reduced significantly. XPS analysis also we did to confirm the presence of Fe and the form of Fe which is present in the composite. So we could see that Fe present in the matrix in form of Fe metal, not FeO. Again, we also studied the recyclability, because reusability of the catalyst also we studied. We have done it for 5 cycles, repeated use of the same catalyst, regenerate and reuse it. We could see from the figure which you can see, there is a slight change in the production. Otherwise, but production is quite good up to 5 cycles. Then this same catalyst also we used for the Rhodamine-B degradation, and the result is shown here, which also shows that 7.5 weight percent Fe-doped catalyst gives highest reduction. The graph is between C by C0 versus time. So C by C0 is lowest, means the percentage degradation is high. So the highest photocatalytic activity was obtained with the 7.5 FeSnO2. This result was agreement with the both of the PL spectra and UVD. So in conclusion, Fe-doped SnO2 photocatalysts were synthesized using hydrothermal synthesis method at high temperature and pressure. Among the prepared catalysts, 7.5 Fe exhibit the highest visible light photocatalytic S2 production rate, which is 18.8 micromole per hour, and this also we compared with the literature, which shows us 3 times higher, which gives us 3 times higher than the SnO2 which is reported before. And this higher amount of hydrogen producer can be attributed to the reduced size, which we have seen in SEM, reduced charge recombination, and also the band gap. 7.5 Fe showed excellent degradation capacity for Rhodamine-B dye under sunlight within 60 minutes. The recyclability study showed that the photocatalyst can effectively used up to 5 cycles. So that's all from my side. Thank you.